we have represented our functions as mappings, as set of ordered pairs, and as equations. Now, these three, so far, we already have ideas as to how to determine if these relations are indeed functions. But the last one would be graphs. An example of graphs would be this one here. We have three different graphs, and we ask ourselves, are these functions? So, going back, we have to make sure that one, let's place it here, one, all x's are used, and then for each x has one y. So let's illustrate. If we can see here, assuming that our graphs extends indefinitely for this one, we can see that all x's are used. When we say all x's are used, the graph each has a counterpart on our x-axis. And as we can see, there is no hole, line, space that would say that that space is not part of this graph, not part of this relation that is in our x-axis. Therefore, all x's are used for this one. Let's check if each x has one y. Let's clear that out. Now, if each x has one y, for example, this specific x value here has more than one y rather, then there should be another red or another part of the graph here somewhere. But since there's none, that means for this specific x, this is the only y that it has, that red part of the graph. Similar to this x. This x only has this specific y, and it doesn't have anything else, which are red, which are part of the graph. Therefore, before we have our conclusion, it's the same for -1 and all the other x's here. Therefore, we can say that the first one is a function. Will it work in the second and the third graphs? Pause the video and try to analyze and answer that if these, the second and third graphs, are functions. So, checking for the second graph, if we're going to see if all x's are used, if this continues, then we know, if you still remember your high school mathematics, that this graph actually continues indefinitely, it continues to expand, and it would still have connection somehow to the x-axis, meaning all values of x in the x-axis would have a corresponding point in the parabola. And each of them only has one y, meaning this specific x has this specific y only. This specific x rather has this specific y. This one has this specific y. Therefore, this is also a graph of a function. However, for the third one, we can see that this is an oval or an oblong or a near circular like figure, and it ends here. These x's here are not used anymore. Therefore, this alone will give us a hint that this might not be a function. However, we have to point out that this might be just like a set of ordered pairs, that what we mentioned a while ago, that those who are not part of it are not really mentioned. So, we have to check if each x has one y instead. And as we can see, for this specific x, it has this y and this y. That's why this is not a function. Again, just to clarify, Even though these ones are not here, we cannot necessarily say that this one is violated, the all x's are used are violated, because this might be just a set of ordered pairs in which the others are not really part. And we're going to talk about that in a later lesson. Now, there is an easier way of determining if graphs are actually functions, apart from doing this manually and doing this and doing this though will take a long time. So instead, we can do the vertical line test. If it is possible for a vertical line to intersect a graph at more than one point, then the graph is not the graph of a function. Say for example, this one. If this line here will be touching more than 2 points in this set of ordered pairs, then this is not a function. So let's see. Did you see it? As you might have noticed, when the vertical line passed by here, it passed by 2 points, this point and this point. Therefore, this relation is not a function. There you go. How about for this one? Pause the video and try to see if this is a function. So, let's pass that green vertical line, and as you can see, it only passed through one of the points only once. Sorry. Therefore, since the vertical line passed through just that point and no other point, this relation is a function. How about this one? Pause the video and try to see if this is a function or not. So, here's our vertical line, which can be your pencil. And as you can see, it passed by without passing through any 2 points in our graph. Therefore, this is a function. How about this one? Is this a function? Pause the video and analyze. So, here is our pencil that serves as our vertical line. And take a look. As we can see, the pencil actually passes 1, 2, 3 points in our graph. And since it passes not just one, but more than one, then this is not a function. To sum it all up, to determine if a relation is a function, we have to make sure first that we understand that a function can be represented as a mapping or a set of ordered pairs, It can be an equation, and it can be also a graph. The set of ordered pairs can also be likened to our table of values. And always remember that if it's a function, it will always rely on the fact that all x's should be used, and each x should have one partner. And we will be having different ways of knowing whether the relation is a function. The mapping is directly using the definition. The set of ordered pairs in the table of values rely on the x coordinates. The equation relies on the exponent of y. And the graphs rely on the vertical line test.